So welcome, everyone. I'm delighted to kick off the spring seminar series with introducing our annual PH lecture, which this year is Anna Bonica from Carnegie. So as a backdrop, for those of you who may not be familiar with the PH lecture, as it's called, the PH lecture is an endowed lecture that we hold essentially every year. It was established by the Hertelindi family of California, and Dr. Hertelindi, Paul Hertelindi, was an alumni member of the Smithsonian National Board. And for several years, he served as its official liaison to SAO. So the family, in fact, established this lecture to encourage and celebrate the observatory's outstanding young scientists. And of course, this year we have an extremely outstanding scientist in Anna. So this has been held, or began in 2006. The first lecture was given by our own Alexei Vaklinin, a number of people you'll recognize on the list, including Sean Andrews, Karin Oberg, and last year, our own Janice Samra. So this year it'll be Anna, and those of you who know her know that she recently transitioned to a staff position at Carnegie Observatories, and her specialty is stellar dynamics, and her research aims to uncover the structure and evolution of our galaxy, the Milky Way, especially in dark matter halo that surrounds it. And her research, she uses both space and ground-based telescopes to measure the motion of stars and constructs numerical experiments to discover how dark matter affects them. So Anna received her master's in physics from the University of Grabeg in Croatia in 2010, and her PhD in astronomy from Yale in 2016. She's a fellow was a fellow at the ITC here at the CFA before moving in September of this past year to Carnegie. So we're delighted to have her and hear more about her work, the title of which is Weaving the Milky Way Tapestry. So Anna, over to you, and congratulations.
Thanks, Mike. Thank you all for coming. Thanks, Paul, for this award. Really happy to be here in this capacity. As I hope you'll see in the next 40 minutes or so, I had a great time at the CFA, and this time was really kind of kicked off by a big change in the way we look at our own galaxy, the Milky Way. So I started, as Mike mentioned, in the fall of 2016, and this is when the first data release from the Gaia mission happened. And of course, like the first one wasn't really all that changing. It didn't have as much of an impact as some other releases, but it was kind of a signature of bigger things to come. And just to kind of give a brief overview of the data release that actually changed the way we look at the Milky Way, it was the Gaia data release 2. And here just some of the numbers of what this data release contained. So Gaia is an mainly astrometric mission, but has also spectrometers. So most of the data products, at least at the time in 2018, when the data release 2 happened, was to provide the positions and brightnesses of almost 2 billion stars and parallax proper motions for also for most of them. And so you can see that some of the Gaia team provided a lot of other studies like the surface temperatures and some other stellar properties for those stars. But as you can see with the sizes of the circles, there is like one that is kind of much smaller than the other ones, and this is this one with the radial velocities. And even though it does have 7 million objects that had a measurement of radial velocity in Gaia data release 2, this is really small compared to all the other measurements that happened. And so this means that the stars for which we could have or a measurement of both the 3D position and the 3D velocity in the Milky Way was confined really to the very inner part of the galaxy close to the sun. And as Mike mentioned, I am mostly interested in studying the Milky Way's halo. And so we really wanted to push to the larger distances. And as a part of that, I was really happy to be at the CFA at this time, because then with Charlie Conroy, we started the H3 survey. So, but H3 is a spectroscopic survey done on the Hector-Shell instrument on MMT. And what we are aiming to do is really map the distant regions of the galaxy, the Milky Way halo, at magnitudes beyond those that Gaia provides, so between 16 and 18 magnitude. And so here is kind of showing our targeting strategy overplotted on the Gaia footprint. So we have the started back in September of 2017 and see kind of how we're filling out the sky. We're really focusing on these high latitude regions, so we're avoiding the disk plane. And then been all going on for some time. Then the COVID hit and the instrument failure where not much was happening, but then the tech was really nice. And then they gave us a lot of the time in the past couple of months. So we really made up a lot of ground. And so much so that you can see that at least in this region towards the anti-center, we actually had to start going to these lower galactic latitudes because we almost fill out our footprint in the southern galactic hemisphere as was observable from MMT. And so this is really exciting because now with H3 we have almost 200,000 spectra. So this shows our survey coverage until December 2021. And all of this data is produced by a local team. And I'll mention here the work done by Phil Cargill, who is really doing excellent job of analyzing all of the spectra we're collecting. So they're shown here in the RB31 window. It's a high resolution of 30K, which means that we can measure really precise radial velocities. So the 95th percentile in our catalog has radial velocity uncertainty of 1 kilometer per second. But this is not all. Like what Phil was a very innovative part of like this data reduction that Phil developed is not only using spectra, but using spectra simultaneously with the photometric data. And what this allows us to is to better constrain the overall properties of the star, and in particular its luminosity, which then helps us get a much better handle on the distance than what is available from Gaia alone. And this is really important for these distant stars in the halo, because the parallaxes are, well, not very good at those distances, but again, 90th percentile in the log is 20% relative distance error. So now it's a really unique data set and very exciting one for studies of the stellar halo. And so just to visualize what we're finding here, I will show orbits of a random sample of 100 stars from the H3 survey. So again, starting with a Gaia image of the sky, and then seeing how these stars are integrating their orbits forward in time. And the color coding here is by distance, as marked on the color bar on the and an important thing here to note is that there are a number of stars at large distances. And so one of the very first papers that came out of H3 is by Denis Zaritsky, who had taken these very distant stars beyond 60 kiloparsecs and used their motions to estimate, or rather put the lower limit on the mass of the Milky Way. It turned up being fairly high, meaning that it's a very massive galaxy. And then just a few months ago, graduate student at University of Toronto working with Josh Spiegel, that probably many of you remember, has analyzed a full sample of H3 stars orbiting the halo, and from their motions derived I think is the most precise measurement of the mass of the Milky Way to be 10 times to 12 solar masses. And so this precision of the order of 10% is really a breakthrough, because for like decades, we have kind of, the uncertainty has been a factor of several. So really what H3 as a survey did here is provide this unbiased sample of stars precisely measured throughout the halo that allowed this measurement to be made. And so this is something that some of the first things we can do is see kind of how fast the stars are moving toward the halo and measure sort of the enclosed mass. Another thing that kind of pops in or may have popped into your eyes on this figure is that the distribution of these orbits is not random. So there's sort of like what looks like a highway going through the Milky Way halo. And these, in fact, are stars that are part of the Sagittarius stream. And this is a known structure that has been discovered more than 20 years ago and has been studied in a lot of detail. So I will start here with the latest view of the Sagittarius stellar stream in the Gaia data. So these are all stars that were stripped from the Sagittarius dwarf galaxy, and sort of on the top panel, I'm showing their positions in the sky, just kind of oriented in a coordinate system that is aligned with the orbital plane of Sagittarius. So you can see that like close to the dwarf, there's a large number of stars, and then still very many at somewhat lower densities, kind of wrapping around all the way more than 360 degrees. And with Gaia, so because there are so many stars, there are like some, they're also luminous enough to have a spectrum in Gaia. So on the bottom plot, I'm showing the radial velocity measurement. And this data is really very exquisite, kind of a great playing ground for dynamical models of disruptions of dwarf galaxies in the Milky Way. So what Eugene Vasiliev, who led this paper, did is take this data and then also created a dynamical model of disruption of a dwarf galaxy that kind of matches this data. And so I will overplot it next. So these are the colored points going from black to yellow. And the model here is colored by the stripping time. So basically how much time has passed since those stars were stripped from the Sagittarius dwarf galaxy. So you can see that the part of the stream that has been mapped in the Gaia data is really very well matched by this model. But it also means that it implies that all of these stars have been stripped in the last giga-year or so. And this is where an interesting part comes in from the H3 survey. So when Ben Johnson was analyzing Sagittarius data and found a different way to select stars to Sagittarius, he also recovered this trend of positions of Sagittarius stars on the sky and also their radial velocity trends. So these are shown in the darker blue points. But what Ben also found is that there's what looks to be a kinematically hotter population of Sagittarius stars. And you'll see from the dates, like Ben's paper came out in 2020. And then at the time, this was before Eugene's model. And so at the time, we just hypothesized that maybe these are some older stars that were stripped before at some much earlier time from the Sagittarius dwarf galaxy, and they are now kind of a more phase mixed into the rest of the Milky Way halo. And the exciting part is, at least it was for me when I made this figure, is that actually these stars really align very well with the model predictions for these earlier stripping episodes of the Sagittarius dwarf galaxy. So really tracing them here in the space of the radial velocities. So I think this is really exciting because it means that we can, with this kind of data, we can start unwrapping even the more distant things in the past that came onto the Milky Way. And a way to more formally extract that information was actually proposed more than 20 years ago by Amina Helmi. And so as we saw in the case of Sagittarius, we do expect merger events to kind of slowly mix into the halo. But we'll see that there is a way to still extract that information once we have the 60 phase space of stars. So I will show this in a movie where on the left panel, there will be dwarf galaxies merging onto the Milky Way, and the disk and the position of the sun are marked here in orange. And on the right panel, I'll be showing the energy and angular momentum of these stars. you can see as a dwarf galaxy comes into the Milky Way, it loses its stars and it kind of mixes out, stretches around in the halo. However, because at least in this model, the energy is conserved, so our gravitational potential is not changing, and it's axisymmetric, so also the angular momentum perpendicular to the disk is preserved. You can see that all of those stars, once they are released from the dwarf galaxy, they remain at the same place. So even when we get other younger accretion events, even when they kind of mix out, and it would be hard to tell them apart spatially, they're very distinct in this phase space of energy and angular momentum. And so, of course, this idea was proposed a long time ago, but it took a couple of decades for it to mature and for the data to become available for us to actually calculate the energy and angular momentum, which is exactly what God provided us, and H3 in additional numbers providing this sixth component of the phase space in radial velocity. So kind of moving on from this cartoon picture into the view of the Milky Way by Gaia and H3, we come to the work of Harvard graduate student Rohan Naidu. So a couple of years ago, Rohan was analyzing all of the giant stars in the then data set of H3. And on the left hand, I'm again showing them in this XZ projection, again, marked with a star symbol. So you can see that we get, well, we are excluding this, but we get at tens of kiloparsecs distance. And this is fairly well mixed in those positions or kind of configuration space. But when you look at the energy angular momentum plane, we see that there is a lot of structure in this. So it's not a uniform distribution, which again is exactly kind of what we would have expected if the halo was built up of smaller dwarf galaxies merging onto the Milky Way. And this has been sort of a fertile hunting ground for discovering these Milky Way progenitors. So well, I was about to say our very own, but I'm not at the CFA anymore. So CFA's very own fellow Qiu Chulmyong also discovered a couple of progenitors here in the Sequoia and again Enceladus, and there have been several others, including Sagittarius. But what Rohan did is a really careful analysis, kind of attributing all of the stars in phase space in not just energy and angular momentum, but also actions and chemical properties. So he tagged all of the stars being part of the same progenitor. And what he ended up with is a sample of a dozen progenitors. And as you can see, now these are all colored points. So they're like mainly confined in different regions of this phase space diagram. And what is, I think, the most striking result here is that there are very little uncolored points. So what Rohan was able to do is assign origin for almost 90% of the stars in this sample. So really showing the promise being delivered here that we will be able to find the origin of most of the stars in the Milky Way halo. And so to kind of bring us back to the figure that I started the talk with, so this is some of the structures that are kind of best populated in H3, shown in the orbital space of the Milky Way. And so what H3 and the Gaia survey, and basically in the Milky Way halo, provides us is the two frontiers. And on the one side, we have the dark matter question. We saw that now with this precise data on the motions of stars, we were able to estimate precisely the total mass of the galaxy and find that only 10% is what is all of the stars that we can see, and 90% is something dark. So with these new measurements, we kind of have a chance of making the Milky Way halo as a dark matter laboratory in which we can study properties of the distribution of dark matter in a lot of detail. the other frontier is understanding a little bit more about these galaxies that kind of made it into the Milky Way. These are some of the earliest galaxies that were formed in the universe, and here we can kind of observe them at star-by-star basis. So it's a very complementary frontier to the James Webb observations that will be starting very soon. So there's a lot of material here for way more than for one talk. So in the H3 side, Rohan really has been the person who has been pushing the frontier on the first galaxies, and I'm sure you will hear a lot more about this side of research in a few months at his thesis defense. But as for this talk, we'll be focusing on dark matter. And kind of what we want to do in this line of research is understand what is the small scale structure of dark matter halo in the Milky Way. The reason for asking this question is illustrated in this slide, where I'm showing the 3 different models of dark matter and the shape or internal structure of a dark matter halo in each of them. So on the kind of vanilla, like standard cosmology side, we have a cold dark matter halo where particle mass is on the order of GeV, and a halo is filled with a lot of substructure, the smaller subhalos. And as you just heard, we know that the Milky Way stellar halo is also made up of substructure, but way fewer of those because most of these are expected to be dark or rather devoid of stars. So we are expecting in this model to have a large population of dark matter subhalos kind of roaming around. These are people have been looking for them for a while and came up short. So other models that don't produce so much substructure were proposed, such as the warmer dark matter models, where the particle mass is on the order of KV, but otherwise has similar properties like CDM. And so the main difference here being that there is fewer subhalos. And then a model that has gain popularity recently is a so-called class of fuzzy dark matter models, where the dark matter particle is at a very low mass, such that the quantum properties become discernible on astrophysical scales. And this is a simulation also done by the CFA alum, Philip Motz, a few years back. And so the goal of my research is to understand what the dark matter halo of the Milky Way looks like, whether we can make a distinction between these models. And my tracers of choice are tidally dissolving globular clusters. So to show why, I'll show a simulation of a globular cluster being merged into the Milky Way. And again, I'm showing here this in the kind of projection, such as the disk is shown as a line, and this sun position of sun is marked with a star. So as globular cluster moves around the Milky Way, it also undergoes some internal evolution. 2 stars often can come close to each other. It's a very dense system, and one can gain enough energy to leave the cluster. As these stars kind of continually leave the cluster, they form this very thin and long tidal tails because they basically only just made it past the being bound to the globular cluster, so they still retain a fairly similar orbit. And this is an important distinction from the more streams of dwarf galaxies. You saw them before, they become all very wide and kinematically hot, but the globular clusters really should remain very kinematically cold. And this is the feature that makes them really good probes of the underlying gravitational potential. So to visualize that, I'm here showing 2 stellar streams simulated on a same effective orbit. Just one was simulated in a smooth gravitational potential. This is shown on top, and the other one again on the same orbit, but in a live cosmological dark matter halo from the Via Lactea 2 simulation. And you can see that the general shape of the streams is fairly similar, but there is a lot more structure in the second one. So during these interactions with dark matter subhalos, some of the stars are kind of longer up the stream. Some of the parts were made overdense, some were made kind of underdense, and this here there looks to be the part of the stream that's kind of detached from the rest of the stream. And so this is kind of the experiment that we want to do. Want to see what the streams look like in the Milky Way, and hopefully conclude something about the nature of dark matter. If we find features, it'll be likely that it's cold, and if all the streams look smooth, it's probably mean that there is not much substructure in the dark matter halo of the Milky Way. And excitingly, now we have the observations to our observational data to start making very detailed maps of many different stellar streams in the Milky Way. So here I'll build a gallery starting with JLM, which is stream discovered in the Dark Energy Survey, and here cross-match with the Gaia data to provide to do a proper motion selection. And so peeling off like most of the Milky Way foreground, we see that the stream that was in the DS just discovered as a kind of single linear structure on the sky appears to have two density components. One is like very thin and dense, and then there's this wider envelope beyond it. So this already shows that perhaps some sort of dynamical perturbation must have happened to introduce this shape. Then moving on to globular cluster Palomar 5 and its tidal tails, we see that even though they're looking fairly regular kind of spatially, there are still large density variations. There's some diversity here in the trailing tail, and then followed by a large underdensity, and then smaller underdensity here in the leading tail. And something that we were most puzzled by is that it looks like this leading tail is much shorter than the trailing tail, and then they also becomes much wider here. And so something was happened here. In principle, we would expect the tidal tails to be symmetric on either side of the globular cluster. And finally, like as a last example here on this slide, I'm showing what were discovered as two streams, the Atlas stream and the Alika-Uma stream. So these were discovered in photometric surveys and appears to be close on the sky, but like separated by a few degrees, so discovered as separate entities. But then when Teng Li went to get radial velocities, she found that there's a consistent radial velocity gradient going from Atlas to Alika-Uma stream, and that likely these were part of the same structure that was after some sort of dynamical perturbation, again separated into two. And so here, and this is, okay, there are a few more cases here, but not that many more. So it's still like a wide open field here. And you already see a different variety of ways that the dynamical perturbations can manifest themselves in the shapes of stellar streams. So what I'm particularly excited about is our prospect of modeling these perturbations. And here I'm showing a model of the GD1 stellar stream encountering a compact massive object that when passes through stream gives a velocity kick to the nearest stars, which kind of opens up the gap in the stream, and like this kick of stars kind of precess around the main orbit of the stream. And so when we kind of look at it in detail, we see that there is this kind of underdensity and a tail of stars being offset from the mainstream. And this model was created to match some of the observational data of the GD1 stellar stream that Adrian Preisvilla and I studied back in 2018 with the second year of Gaia data. So on the top, we're showing the likely members of GD1. So again, a lot of features, like a very prominent density variation. So something like an underdensity at this -20 degrees and -4 degrees, which are again just sky coordinates in the GD1 reference frame. But excitingly, there are also these stars on kind of offset from the mainstream, and the spur of stars and this appears to be an associated underdensity or a gap of stars are really well reproduced by the model that you of a stream being impacted by a compact object that you just saw forming. So there's like the gap at the right place, at the right size, and also this square of stars of the right, roughly the right scale. And excitingly, this the properties of this impact were in this cosmologically interesting regime. So the mass of the impactor was 5 million solar masses. It was somewhat compact and kind of very close to moving at a typical halo velocity. So what we really want to know is, what was it? Was it really a dark matter subhalo, or was it something else that maybe is has less of a cosmological importance? So to explore fully the kind of the constraints that this data provides, we modeled this region and constrained different impact models with the properties of the gap and the spur of the stars. And what I'm showing here are the constraints we obtain on the mass of the impactor and the size of the impactor. So these are the gray shaded region is the region of the parameter space where we find our perturber models of the GD1. And on the color points are the different objects that are known to orbit the Milky Way. So we have the molecular clouds and stars, we have the globular clusters as triangles, and we also have the dwarf galaxies as squares. And dark matter subhalos in lambda CDM are predicted to be in this teal band with the dotted lines showing the 1, 2, and 3 sigma dispersion from the mass concentration relation. And so when you kind of look at this at face value, like you see like, oh, well, there's this nice overlap with the massive globular clusters that are kind of compact enough to produce the feature that we see. However, what Giles provided us are the orbits of globular clusters, and when we integrated them back, we didn't really find any matches, any globular clusters that come close enough to the stream to cause the impact. And this was the case also for the molecular clouds and the dwarf galaxies. So kind of on orbital grounds, we can exclude these luminous objects. And then what we are kind of left with is a very, very empty looking plot. So some of the options that we have left, because something happened to GD1, and it looks like it might have been an unseen globular cluster that's maybe hiding now behind a disk, might have been an unusually dense dark matter subhalo. It might also have been a supermassive black hole. Like if we keep our mind very open, we are consistent with a point mass impactor. So so these are like some of the possibilities, and a nice option that we have in the Milky Way is that we can try to predict where the object is in the sky and try to get some additional way to look at it to distinguish between these options. So taking the models, like these same models that reproduce the debris of the GD1 on the sky and forecasting where the perturber would be today, we can get basically a solution anywhere on the sky. However, the color coding here is by the relative radial velocity between the unperturbed part of the stream and that first part of the stream. And so again, thanks to the CFA tag, we got high resolution spectroscopic data on MMT and measured this velocity offset to be smaller than 1 kilometer a second. And then this really narrows down the distribution of points in the sky. Still a lot of ground to search, but going in the right direction. Another iteration of this that we hope to make is with a really precise measurement of the relative proper motion. So here the color coding again by the predicted relative proper motion. And we have an ongoing project with HST. I guess we are really midway through, like in a year from now, we'll be getting the second epoch data to measure these more precise proper motions in order to make this even further narrow down this distribution on the sky. And where we are going with this, I think is very exciting, because in the case where we kind of can localize the whatever the perturber is, we can follow it up in different wavelengths as well. So a paper I had recently with Nestor Mirabal was looking at some Fermi unclassified sources that have properties consistent with being dark matter subhalo candidates. And so these are now overfloated as open blue circles here. It's still kind of early days, more of a proof of principle, but I think it's a very exciting prospect to be kind of combining these different frozen searches for dark matter substructure. But one kind of big caveat in all of this orbit integrations and kind of prediction of where objects are at the present is kind of what we assume for the underlying gravitational potential. And most of the modeling that has been done overall in the field so far, and all of the modeling this talk, has assumed that this underlying gravitational potential is like something very simple that can be described with an analytic function, and it is not changing in time. So in this case, yeah, we have like a very simple system, and anything new that happens is this perturbation that can be attributed to interesting physics. However, like at the beginning of the talk, I showed that like now we have inferred when that Milky Way has been accreting dwarf galaxies, and couple of years ago, Dietrich Rosen measured exactly when those mergers happened. And so the question is then, how does this affect our ability to trace orbits back in time? And looks like it might, well, depending on the mass of the dwarf galaxy being accreted, it might be a lot. So here is almost a cautionary tale. Showing a simulation of LMC merging onto the Milky Way galaxy. So this is something that is really going on at the very moment as we speak. And so this is a final snapshot of simulation run by Nico Gamargo from Gertina Besla's group in Arizona. And so you can see that like the underlying distribution of dark matter is really asymmetric and reacted to the income of the massive dwarf galaxy by producing this sort of global response kind of ahead of the orbit, and this local density wake kind of behind the orbit. And this is a prediction of a theoretical prediction of kind of what the outer stellar halo of the Milky Way should look like. And as for the actual observation, Charlie had a paper last year where he mapped out K-chance between 60 and 100 kiloparsecs with a cross match of Gaia and Wise. And what he found is that indeed the outer Milky Way is very asymmetric, and it actually maps this predictions of the global response and the local wake really well to what we expect from Nico's simulation of the LMC merging in. So this already kind of puts us in an uncomfortable position, or rather may be severely limiting our the accuracy of orbital calculations if we are not accounting for this effect. But still, this is kind of happening in the outer halo, so I thought like maybe we should still be fine in the kind of inner 20 kiloparsecs or so. But then recent work has shown that even the inner parts of the Milky Way may have a really good memory of all of these past events that happened. And so where it came from is, again, from the shape of the stellar halo that in 2019, from the distribution of R. Lyrae, Juliana Iorio, and Vasily Belokorov have measured that it is kind of elongated and not aligned with the Milky Way disk. So it's kind of at some tilt. And last year, Rohan Naidu explained this shape by a merger of the most massive past dwarf galaxy to have been accreted onto the Milky Way, the Gaia Sausage Enceladus event. So by matching, so I mean, what Rohan did was create a numerical simulation that reproduces the observed distribution of sausage and cell of the stars in the phase space as observed by H3, and then saw what the kind of compared the resulting stellar distribution to the one of the measured with our LIRA stars, and found a really good match. And so this is really striking because that merger happened 10 billion years ago. So it looks like that really this memory is very long, that the stars didn't fully realign themselves with the rest of the kind of Milky Way symmetry. And then just this question of timescale was a little bit unusual. I think everyone's intuition would have been that in 10 billion years, everything should have mixed. But then Harvard graduate student Jesse Han recently provided, or rather, it's still work in progress, but seems to have found the answer. So what Jesse did was take the stellar particles from Rohan simulation and then simulated their evolution in a kind of true potential, which is actually structured. It's follows basically the stellar distribution pretty well. On the left-hand side and on the right-hand side is starting with the same initial snapshot, but integrating the orbit in a spherical potential. And so you can see that if in this assumption of a spherical potential, this distribution really sphericalizes as well. However, in the tilted potential, it stays tilted. And so this means that even in the inner galaxy, we might have complexities in the distribution of dark matter that needs to be taken into account if we were ever to do precise orbit integrations. And so now this is kind of a point where we need to ask is, everything is looking so messy and complicated. Is this really a lost cause? Can we, is it really just doomed to fail? But I will provide a couple of slides now arguing that there are some good news on the horizon and that there is some regularity to this underlying complexity. And it again comes back to this phase space. So starting with the phase space of H3 stars and the energy and angular momentum, early last year, we published a paper on placing the stellar streams into this, this space. And so when we did that, we found that the stellar streams themselves were kind of clustered in the same regions where Rohan found dwarf debris from dwarf galaxies to be clustered. So what this implies is that the stellar streams, the different stellar streams of these globular clusters also came in as a part of those dwarf galaxies that were created on the Milky Way. And as a part of that, that means that they are more likely associated with some other objects that were brought in by those same dwarf galaxies. And so one immediate kind of corollary of this finding is that we actually then found a lot of progenitors of what appear to be stellar streams without one. So what I'm showing on the right are likely members of the different stellar streams, and they are named and colored in different points. And then some of these matches with globular cluster orbits that we have found. So the crosses mark the globular clusters, and the lines are orbits drawn from their position and velocity uncertainties today. And you can see that many of them cross through these globular cluster streams, and some spanning very large kind of angles on the sky. And so this was, apart from being an interesting puzzle as to why we missed out these parts, like why there are no stars or the much lower density, this is a really exciting prospect on a couple of accounts. The first one being that now we have sort of a very long lever arm for constraining the overall gravitational potential. So a couple of years ago, I conducted formal study into the information content of stellar streams with David Hogg. And what we found is that the longer a stream is, the more precise constraints on the underlying gravitational potential it can provide. So having these like very, very distant stars, or stars very distant from the globular cluster, means that they will be very informative. And another aspect of the study was that we found that jointly streams can provide much more precise information than any single stream. So kind of a joint analysis of on the order of 10 cell streams should provide measurements of properties of the gravitational potential with a better than 1% precision. And so this is maybe like a step in the right direction, that even if we, like, the underlying gravitational potential is kind of complex and evolving, that we do have now this very precise gravitational antennae with which we can map it out. And then what kind of remains to be done is to kind of build a machinery to actually be able to do such a complex inference. And then a second corollary I wanted to mention is one that at least shifted how I think about kind of encounters that streams could have had with other objects in the halo. So remember when we said that in principle GD1 could have been hit by a black hole or supermassive black hole? Well, now this actually looks like a possibility. If it came with a dwarf galaxy and then nuclear star cluster or a supermassive black hole of that dwarf galaxy, they would be coming on a similar orbit and potentially would have had some likelihood of interacting. Of course, we don't know where those black holes are, but we do know where globular clusters are. So in the very last slide, I will kind of show some work pretty much in progress, showing kind of removing our preconceptions of thinking that globular clusters would have been too unlikely to impact the GD1 stellar stream, kind of starting with the other way around, kind of what would it take for a globular cluster to have impacted the GD1? And so what I'm showing here on the left-hand side is a corner plot of samples of the present-day positions, or rather velocities and parallaxes of NGC 1851. And they were chosen such that they minimize a distance from GD1 at some point in the past. So we started like this search and measured position of the cluster, which is marked in blue, and then kind of let it go, taking the measurement uncertainties as priors on these. As you can see that there, like the shift, like after the burn-in period, actually moves, it finds a solution and samples it rather well. And excitingly, the solution comes really close to GD1. So here is for the best fit solution, distance as a function of time. And you can see that something like 500 million years ago, in this solution, the globular cluster came within a parsec from the GD1 stellar stream. And this is really just kind of fresh off the press, like a visualization of that encounter. It looks like that it would indeed pull out stars, maybe like slightly more than what we see in GD1, but kind of the general morphology is pretty similar. So it has like this opening and the gap, and then like a spur of stars, kind of at positive phi2 and more positive phi1 coordinates. So I think this is very exciting as a prospect. Maybe does add more complexities to the kind of needing to account for possible interactions with globular clusters when we are looking for dark matter substructure. But I think if we can convince ourselves that this impact happened, I think this is we'll be able to make a really precise measurement of kind of this dynamical system. And this, in general, I feel bodes well for what we will be able to do with dark objects as well. And to wrap up, we have a lot more streams to cover. So here I'm just zooming out from the inner part of the galaxy and kind of cycling through the different streams that have Gaia orbits measured. You can see that they're exploring the different parts of the galaxies, and hopefully each of them holds a special message of its own. And A huge thanks now goes to Brian and Clea and all of the staff at Las Campanas. Yesterday, we had the very first night of the MegaChem run to observe one of these very outermost globular cluster streams called the jet stellar stream. And we are really kind of pushing into this unknown dark matter dominated region of the galaxy. And I'm sure we'll be finding a lot of interesting stuff. So with that, I'll thank you and take any questions.
Thank you so much, Anna. That's a very impressive presentation, both the observations, space and ground-based, and the simulations and modeling. So
thanks.
Very, very well done. Do we have questions? Well, we had the raise hand feature. Kareem.
Hi, Anna. Good to see
Hi,
you.
Kareem.
Very nice talk. I was wondering, is GD1 kind of is it unlucky that it had a chance of encountering another globular cluster, in the sense that there are other ones that are less likely to have encountered one, or is this just a natural consequence of many globular clusters coming in at the same time, such that it's sort of a generic worry for probing cosmology?
Yeah, I think it might be a generic worry. Like that being said, like GD1 is like here in this cluster of retrograde streams, and there is some low mass dwarf galaxies that came on retrograde orbits. So maybe it is kind of it won't surprise me that it did have kind of correlated orbit with some of the other debris coming in here. That being said, there may be kind of regions of this space that are kind of more prone to, say, interactions with dark matter subhalos rather than with globular clusters. And yeah, I think this is another like very nice question to be addressed with analyzing simulations like what Lars's group is running, to kind of see on what sort of orbits we get what sort of interaction probabilities for it, like with different kinds of objects, like rather be it like the bar, the molecular clouds, globular clusters, or dark matter subhalos. So yeah, I think I don't see GD1 as being like particularly special in that regard. If anything, it might have been kind of a safer object because it's retrograde, whereas most of the other globular clusters are kind of prograde. But yeah, so I'd say it's maybe a generic worry.
Thank you.
Thank you. Roseanne?
Well, I had a similar question, but the opposite way around. I was more concerned with the effect on the globular clusters. So if globular clusters are prone to this type of interaction, how frequently would one expect a globular cluster to undergo this, and what would be the long-term effects if it happens many times during its lifetime?
Yeah, that's a really interesting question, and there actually has been some work on, well, not exactly that, but related. So I think it will be helpful to discuss it. So, and it was really motivated by features that look like this, what we showed in the Jalon stellar stream, where there's this kind of wider envelope of stuff. So one proposal that has been numerically explored in some detail, and actually there's a paper on the archive even today, kind of suggesting that part of like this structure came to be in the early unwrapping of a globular cluster, when it was still in its parent dwarf galaxy, that some of the stars were kind of tidally dissolved or tidally stripped there, and then came on a kind of a slightly hotter orbits under the Milky Way. Once it's stripped into the Milky Way, like those stars kind of formed as part of the wider envelope. So I think, so this is not exactly the question you were asking, so, or at least not the way I understood it, but I think the similar phenomenon might be happening, that there would be like this enhanced stripping of stars that might show up as this in these wider envelopes that are slightly more kinematically hot than what we would naively expect in just kind of tidal evaporation, like of the due to the two-body encounters in the globular cluster.
Well, that's very interesting. Thank you, and it's great to see you in your new environment.
Thanks, Roseanne.
Alyssa?
Oh, thank you. Hang on. Oh, good. I am unmuted. Thanks, Anna. That was really lovely. And I know you and most of the people listening care about dark matter and large things and outside the galaxy, but some of us are wondering what these interactions do to the actual disk of the Milky Way itself. Do you have an idea?
Oh, I have a, I have a theory that it's something interesting might be happening. I didn't really have time to follow it up, but and it has to do with the more massive mergers. I would imagine like a globular cluster plunging through the disk like would probably not like have a, I don't know, maybe for like triggering star formation, like it actually might have an effect, but like in these dynamical studies, at least I think it is really the dwarf galaxies that have the largest effect. And something that caught my eye in this latest version of the phase space is that kind of what look to be ridges on this side. So the disk stars on kind of disky orbits are on this left-hand envelope. And so these are like the very kind of circular, or, we are observing about the disk, but kind of as here are the thick disk stars basically here. And then what we find here is that it's like very subtle. So, that's like I said, I have a theory, but there seems like there's like an underdensity here, and then kind of more stars here, and then more stars here, and then like depending on how squint, you might find something here. And when I just kind of quickly estimated what is the energy radius of a circular orbit at those energies, I forgot what the numbers were, but then Rohan made a connection that these are the exactly the same radii of the Sagittarius pericentric passage onto its journey around the Milky Way. So what we might be seeing is kind of stars being heated by Sagittarius. And actually there have been studies showing that the bursts of star formation in the Milky Way disk also correspond to the pericentric passages of Sagittarius. And like way back in the past, we also found kind of these thick disk-like stars on kind of halo-like orbits, which we think were kicked on there after the Gaia-Sausage Enceladus merger happened. So I think that's something that really is happening and kind of changing the distribution of the Milky Way disk as well. So I guess I'm personally more excited about this prospect of kind of really being able to precisely disentangle the orbit and of these objects and see kind of what that tells us, if anything, about the distribution of dark matter or any dynamical friction it might have experienced. But I imagine that there also would be a lot of stuff happening with the star formation being triggered in these regions as gas is being compressed and kind of stars being kicked on hotter kinematic orbits as well.
Sure, thank you.
Thanks.
That was a really great talk. I was curious, based on all the stars that you've measured with H3 and orbit integrations you've done, is there any evidence for an existing smooth halo that would have been created in situ when the Milky Way formed? Or is that just a fiction now?
Yeah, that's a very old standing question. So like based on this is the result based on the first year of Gaia data. What we found is that there are stars that are on kind of at a higher metallicity than what we would expect in the halo. So FE over H larger than -1, but they are on halo-like orbits. And it so they basically have the thick disk-like chemistry, but halo eccentricities and yeah, orbits. And what we found is that, like in the subsequent work here by Rohan, so these are the pink stars, high alpha, meaning the thick disk kind of high alpha element abundances. So what Rohan found is that this population kind of peters out around 15 to 20 kiloparsecs at most. So what we think these are stars actually formed in situ, but they are part of the simulation that was kicked up out of the primordial disk by subsequent mergers. And so depending on whether you count that as a formation of a smooth halo or not. So this is kind of the closest we have come to finding in situ stars in the halo. I guess it is an interesting question. So, as I mentioned, yeah, we kind of could account for like 90% of the other stars like to be part of some substructure in H3. It's unclear. We obviously haven't sampled the entire halo, so it might be that like if we move even further away, or maybe closer into the center of the galaxy, maybe that's where those if they exist, those stars should be. So I guess the answer at the present is that no, we haven't, but there's still parameter space left to search for a kind of smooth in situ component of the halo.
Thank you. That's really fascinating. Thanks.
Thanks.
Any last questions? All right. Well, if not, let's all thank Anna again for a beautiful talk. Very, very nice work. So we will continue the seminar. Oh, yeah, we will continue the colloquium in the coming Thursdays. So again, thank you, Anna, very much for a great talk, and wish everyone a good evening.
Thanks for having me. I'll see you all.
Take care.